Okay, good afternoon, everyone. Welcome to ZEBx's Decarb Lunch webinar series. My name is Natalie Douglas, and I'm the ZEBx Program Manager. Today, we have Tom Place, who is a valued CLFBC volunteer and a leading structural engineer in Equilibrium, here to talk to us about minimizing carbon emissions of steel, concrete, mass timber in North America by better understanding the impact of project location, transportation, and the regional availability of materials, and finding ways to avoid unintended negative consequences from green material specifications. Now, before we dive into the content, I'd like to share my thanks for being able to join you all today from the unceded traditional territories of the Musqueam, the Squamish, and the Tsleil-Waututh Nations. I'd also like to share my thanks to the City of Vancouver and North Family Foundation for their financial support that enables these webinars to be offered at no cost to you folks. If you're interested in getting continuing education credits for attending today, please see the information that my colleague Carrie is going to drop into the chat. And please use the chat to comment and ask questions for the presenter, as well as the rest of the audience. We'll use those questions to help guide discussion at the end of the webinar. Now, this is likely the second to last time I'll be giving the ZEBx overview, so do listen close. And I still get questions about this. So I know there's an acronym soup, but bear with us. This tends to help clear things up about what is ZEBx, what is ZEBx, what is CLFBC. So ZEBx is part of a family of programs nested within the federally endowed Zero Emissions Innovation Center, otherwise known as ZEBx, the BC contingent of the Low Carbon Cities Network. ZEBx is part of the Building Decarbonization team and can be understood as the main convener and amplifier of content developed by this whole team. ZEBx is the first point of contact for those who are either unsure of how to approach the world of building decarbonization or want to be updated about everything. Carbon Leadership Forum BC is focused on reducing embodied carbon. B2E is all about facilitating and supporting building electrification. The BC Retrofit Accelerator is offering on-the-ground support to make energy retrofits happen, and Near Zero supports building research. ZEBx compiles and synthesizes content from all those specialist areas to try to ensure we keep the broader picture in mind and don't become siloed. It's important to also recognize that ZEBx is more than just the building decarb team. I have colleagues who specialize in communications, economic transformation, granting, all working towards accelerating decarbonization. With that, I'll pass things over to my colleague Stephanie Dallow, Program Manager of CLFBC, who I'll be co-hosting today's webinar with. She'll provide some information about CLFBC and set the scene ahead of Tom's presentation. My colleague Carrie is also going to launch a poll just to give us a sense for who is in the room today. Over to you, Steph.
Thanks. Awesome. Hi, everyone. So yes, as Natalie just mentioned, CLFBC is a center of excellence for reducing embodied carbon emissions and is focused on the emissions of the material and construction in our buildings. So as we're seeing this growing need to decarbonize and the focus on operational carbon, CLFBC is trying to fill that gap to build capacity and awareness and tools and supporting the development of policies and bylaws for embodied carbon. And we just happened to celebrate our 5-year anniversary this year, just in October. And so we want to thank everyone for the support over the last 5 years, the leadership from the founder, Anthony Pack, and everyone who's been a part of volunteers, the sponsors, the growing industry is really helping us to continue on with that mission of being the center of excellence on embodied carbon and reducing emissions in our buildings. And we had a really great turnout. So thank you for everyone who's able to make it and be a part of that special night. Also, while I have your attention, I wanted to just bring everybody's awareness to the Near Zero 2 program. And we have a few spots remaining there for any builders or designers, if they're here, who work on townhomes or multiplexes, so anything with four residential units or more. So if we are now offering up to $70,000 to reduce the embodied carbon of those larger Part 9 buildings, and for having you share your experiences back to us, because this program really, what we learned from it, will help inform the development of policy and bylaw for the Part 9 buildings. So yeah, check that out. And if you have more questions about that, you could always reach out to myself. And then just before we switch over to Tom, in case some of you didn't know, this presentation was delivered by Tom at Buildex earlier this year and was really well received. There were a lot of great information that came out of it. And, as we continue to focus and understand the emissions of the upfront carbon having a large significant impact, where this presentation is really showing us the emissions related to transportation and material sourcing of where your structural materials are coming from, and how to make sure that we avoid any unintended consequences related to adding emissions rather than reducing them if we're not considering where we're sourcing these materials early enough in the design process. So maybe without holding it any further along, the moment you're here for, I'll just hand it over to Tom. Thanks, Tom.
Perfect. Thanks, Stephanie. Okay. All right. So yeah, as Steph mentioned, this is all about unintended consequences and trying to avoid them when specifying materials and considering embodied carbon emissions in the built environment. So just a very quick introduction. A lot of people on the call will already be familiar with the life cycle stages that we consider when accounting for embodied carbon. So in the red, A1 to 3 is typically what comes from EPDs, so manufacturers declaring what the embodied carbon emissions are of their products as they leave the factory and head to site. And so what you're going to hear about in this talk is largely the A4, the transportation of materials to site, and how where you source your material from can really impact the transportation, and how to account for it, both when designing for low carbon and then when accounting for it in your declarations. So a big part of why it's important and why there's some subtlety to it is that not all transport kilometers are equal. So transporting materials via truck tends to be 6 times more carbon intensive per kilometer when compared to taking them on rail and moving them on water in ships. And from my own experience coming from Europe, where typically transportation for embodied carbon is treated as not especially important, and generally a small portion of the impact, usually below 10%. I was quite surprised when I moved to North America to realize the transport distances that exist in this continent, which mean some of those stories of ignoring transport or it being limited aren't quite applicable. And in North America, transport is certainly a much bigger part of the picture and why it needs to be considered, and the reason for this presentation. What I'd like to do is step you through the 3 main materials, so mass timber, concrete, and steel, and give you a picture of both the North American context and more specifically what's happening in British Columbia for those 3 materials, and what I'd recommend you consider as part of your projects. So to dive into mass timber, which we have a lot of in the Pacific Northwest, that there are a number of suppliers here. To give people an idea of how mass timber, what's actually happening in the factories and what it's supplied, because if you've not been to a CLT factory, for example, which I imagine most people on this call probably haven't, it's quite interesting to understand that they're all largely following a similar process, highly automated, very efficient, very low amounts of manual material handling. Generally, lumber is going in at one end, and out the other end of the factory is these highly CNC'd bespoke panels. So to sum up that process very briefly, in A1, it's the forestry, effectively the sourcing of the raw lumber, and then A2 being transport from the forest to the sawmill and the CLT plant. So typically either the plant itself will have an adjoining sawmill, or sawmills will be located close to either the supply or to the mass timber factory. And then what we see, and what I'll discuss in more detail, is the A4 transport to site, which is often a much bigger part of the transport impact. So without lingering too long on this slide, what we see is mass timber CLT factories are all of a very similar layout. In one end is coming the raw boards, and out the other end is the CLT, as I say. So to step you through this series of images, starting in the top left. So most CLT factories will take a limited number of board dimensions and grades to kind of simplify their process. So typically 38 millimeter thick laminations in Canada of boards circa 200 to 250 mil wide. And they're then going through an automated grading machine, which is the second image on the top there, identifying where all of the knots are and any imperfections which need to be cut out, then being then sorted, aligned, and finger jointed, all automated in a very fast process, and then cut, so back down to the bottom left, into the standard lengths they need based on the lengths of panels that are being pressed. So these boards travel on conveyor belts through the factory, and they're then cut to length and aligned and glued. And then the second, sorry, the third image on the bottom there is the pressing. So generally there is glue applied, adhesive applied between each layer, pressed, and then a final CNC trimming. There's always a very small amount of wastage, but there is some wastage that typically then gets either pushed back into a kiln for some heat recovery or used as sawdust. But then the final part of the operation is CNCing, then obviously delivery and transport to site. So the North American picture, what we see is there are a number of centers of CLT production. So we have the Pacific Northwest, and there are a number of the original CLT factories that have existed in North America for the longest are located up in the Pacific Northwest. And then there is also a center over on the East Coast in Canada. We've got 2 suppliers there, and then down in the US, in the southeast of the US. So North American production is about 500,000 meters cubed annually. Over in Europe, currently it's about 1.3 million meters cubed. So production is still dominated by European suppliers, but both North America and Europe are growing. North America at the biggest pace. And what you can see on the right of this image is the supply from the various factories. So the Mercer factory in Spokane being the biggest, but we've got a number of large suppliers distributed in each region. What I wanted to highlight was why the suppliers are where they are. So on the left-hand side, that's obviously the locations of the suppliers, and on the right is location of forestry across North America. So what we see is CLT and glulam plants tend to be located close to the supply of the raw material, which makes a lot of sense. But that does then have some challenges for us establishing getting material from source to where it is used. And what we also see is there is some variation in the type of material, the types of wood species used in each location. So Pacific Northwest, we see a lot of Douglas fir used and some spruce. In the northeast of Canada, typically all spruce, and Nordique, the green dot there, use small diameter logs as part of their mass timber because they're higher up in the boreal forest. So the trees are smaller as a result. Then down in the southeast of the US, that's typically the southern yellow pine species subgroups. So most, well, all of those species have similar properties in terms of strength, some small variation, but it's aesthetically some differences as well, which architecturally you need to be aware of. So not all mass timber is absolutely equal. So this graphic is demonstrating a little bit of the challenge of getting wood from source to where it is required in a West Coast context. The red dots are showing the location of lumber mills, And then in blue, we have the CLT plants. The big green dot is the Ferres MPP plant in Oregon. But what I want to highlight to you here is that the major demand on the West Coast sits down in Southern California. And to get lumber from where it is grown through the plants and down to those major population centers, the transportation is approximately 2,000 kilometers. So that is part of the challenge that we face in North America, as I say. I then want to just talk you through some high-level numbers about what that means. So this graph is showing effectively what's contained in the mass timber EPDs across North America, and generally what we see is the A1 to A3 for CLT is largely similar amongst suppliers. There is some variation based on the volumes of material they're able to produce and the electricity grids in the area that those factories are located. But overall, they're generally similar, and I would recommend around about 0.25 kilos of CO2 per cubic meter is a good starting point for people completing early stage LCAs. Why I wanted to introduce that is to link that back up to the transport. So there's quite a lot going on in this table, but I think it's important to understand. So looking at 3 different locations, major cities in North America, and the impact of where CLT is sourced from for those cities strongly will impact the embodied carbon at stage A1 to A4, so including both manufacturing and delivery to site. So the top line is for lumber grown in the Pacific Northwest and delivered to Vancouver. Typically, the transport is going to account for around 20% of the carbon, and overall, there's not a big uplift, and that typically would be captured in a standard LCA. But we see for Vancouver, if instead, for whatever reason, that wood was not sourced from one of the suppliers in the Pacific Northwest, but came from the northeast of the continent, then actually you would jump to more than twice the A1 to A4 impact. And then even more extreme for lumber being sourced from those suppliers down in the southeast of the US, you're getting to almost 3 times the embodied carbon impact purely because of where it's been sourced. And there's a similar story for both New York and Los Angeles. So my advice would be, when you are looking at using mass timber for a project anywhere in North America, establish where the suppliers are, and ideally, obviously account for that in the LCA, but also if there is going to be a big negative impact sourcing from one of the locations, to be highlighting that when the specification and the tendering process is being run through. And I wanted to give you just a bit of a project example of where we've, at Equilibrium, have put this into practice, helping to guide a client to limit the embodied carbon of their mass timbers. So this is a Baker's Place project, which is in Madison, Wisconsin. It's a 14-story residential building, 240,000 square feet, mass timber hybrid. So it's a CLT floors on a steel frame with a concrete podium for the lower 3 levels. So the client came to us and said they were looking at the tendering for the mass timber, and they had 2 potential suppliers that were competitive from a financial standpoint, and they were looking for some advice from Equilibrium in terms of how that stacked up from a structural design perspective and anything else we could add. And the option was to either bring wood from the Pacific Northwest right across the country to Madison, or alternatively use some European supply, which could be sailed all the way in and then transported via truck or train, depending on what was available. So both suppliers produced a functionally equivalent PRG 320 certified CLT. And what we were able to do was looking at the option to either truck 2,700 kilometers from Washington, or alternatively bring it a much further distance, but on boat. And working with the CLT supplier from Austria, we were able to limit the trucking distance to only 390 kilometers for the entire journey. Everything else done on rail and sea, and overall saved 28% on the A1 to A4 carbon by working with the supplier and the client to actively choose the best routes to limit the embodied carbon. So it's a real success story. I had the privilege of going over to the factory in Austria whilst I was back in Europe last summer. A very efficient process, shipping in containers, and then so that building is now topped out on site in Wisconsin. It's been a big success story. It's been inspiring, and I think has encouraged us to really dial into the transport on future projects as well. Okay, so moving on to concrete. So again, give you all a little bit of a background on concrete and its production methods. So concrete embodied carbon is largely governed by cement, and much of the reasons that concrete gets a bad rap is because of the carbon dioxide emissions that occur during the cement production process, and based on the chemical reaction that happens when limestone and clay are fired in a kiln. The CO2 comes out of the exhaust, and Portland cement out the other side. So in Canada, we're producing 13 million tons of cement every single year. And what that looks like is these are the cement plants and their distribution across Canada. So over on the East Coast, there's a large number of cement suppliers, all concentrated kind of in Ontario, Quebec, and close to the coast. Over here on the West Coast, and in particular in BC, where you have two cement plants. So there's the Lafarge and the Heidelberg plant that are both located very close to each other by the Fraser River. And so almost all of the concrete which is consumed in British Columbia will be using cement from those two plants. So to understand what is feasible in terms of your concrete specification, it's in a way, it's quite simple, because you just need to understand the capabilities of those two cement plants. So yeah, they're producing 2 million tons of cement between them in BC, supplying around 120 batching plants. Concrete, so this slide is showing you what concrete is actually made up of. So on the left-hand side is the volumetric ratios approximately of a concrete mix. So largely in concrete, it is gravel or crushed aggregate and sand, and then some water, and around about 10-11% cement. But in terms of, if we look at the right-hand side, it's the sources of the global warming potential, the greenhouse gas emissions from concrete, and it's around 90% of the emissions are related to the cement. So as I say, understanding the cement production is key to understanding concrete's emissions. Some other big takeaway points is that the embodied carbon of your concrete will scale with the strength that you require. So generally, a higher strength concrete needs more cement, and more cement means higher greenhouse gas emissions. So on the left-hand side, that graph is showing with increased mixed strength, increased embodied carbon. And then on the right-hand side, a story that I imagine a lot of people are aware of is adding supplementary cementitious materials, so SCM, into your mix will substitute out some of the cement and will reduce the embodied carbon. So the ideal situation is a low strength mix with some SCM in, but that's not always practical. So SCM is either fly ash or slag right now, and generally slag you can do in slightly higher percentages due to the stability of the mix. Okay, so here is a little graph a graphic which showing the coal-fired power stations in North America, how they've changed over time. So unsurprisingly, over the past decade, we've seen quite a number of coal-fired power stations being decommissioned. And so, as I say, this is, if I jump to this slide, so this is showing, as of 2019, all of the coal-fired power stations that we had in North America and the ones which were set aside for closing. And within Canada, federal and provincial regulations stipulate that beyond 2030, we will have phased out all of our coal power. What that means is obviously from an energy consumption and a grid perspective, it's a positive, but the what is business as usual at the minute to use a byproduct of coal power, which is the fly ash, to reduce the carbon emissions of concrete, will become increasingly more difficult to do as production of fly ash reduces. So this graph shows over the past 20 years in the US, the dark blue bars are the production of fly ash as a byproduct from coal-fired power stations, decreasing over time as those coal power stations have been phased out. And on the bottom is the light blue bars, which is the consumption, which has remained pretty steady. It's not just the concrete industry that uses fly ash, it's also used in the agriculture industry. So increased demand from or concrete, for instance, has not necessarily changed hugely those blue bars, but what we're seeing is we're using more and more of the fly ash that's produced annually. And what happened in previous years, the excess fly ash was dumped typically in ponds. And so now there is a challenge. Part of what is happening in the cement industry is research to establish how much of that dumped fly ash can be recovered and used in concrete. And you'll likely see more of that in the years to come. I'll run through this very quickly. So this is the other SCM available is slag, or ground granulated blast furnace slag, it's also called. So that is a byproduct from blast furnace steel production. This graphic is showing you in green electric arc furnaces that don't produce slag, that use recycled steel, and the red blast furnace or basic oxygen furnace facilities that do produce slag. So there's a real disparity across North America as to where slag is available. So over on the West Coast, there are no blast furnace steel plants, so slag is not produced here. So that obviously has implications in terms of supply of SCM of slag, but it is available. And the reason it is available is because that graphic on the left there is steel production in Asia. So a lot of the slag that we do have over on the West Coast is being shipped across from Asian steel making plants. So Heidelberg have a application out at the minute to build a facility to import and grind that in the Fraser River at their current plant, but that is not yet operational. So the slag that we do have available to us in the Pacific Northwest currently is being imported from China and ground in a facility in Seattle. A few more takeaways in terms of the concrete situation in BC specifically is to say that those two plants located in the Lower Mainland are both producing GUL cement as standard. So that is cement that has blended limestone at a rate of 5 to 15%. What that means is it will act to reduce the greenhouse gas emissions of our concrete by a similar percentage, so around 10% reduction, because we're blending limestone into that cement. It gives an equivalent performance in terms of strength to more typical, historically more typical GU cement, general use cement. But actually what we see is it's helpful somewhat in terms of early age strength gain, and as I say, reduces carbon emissions by 5 to 10%. I just wanted to end on a a kind of a interesting graphic, which is to say, so of the 2 million tons of cement we produce annually in BC, that's enough to produce 15 million tons of reinforced concrete. And in the city of Vancouver, we consume about 1,800 cubic meters of concrete daily. And that's enough to fill the Vancouver Aquatic Centre every single day with the concrete we produce. For those of you that are familiar with Beach Avenue, that's approximately 180 concrete truckloads. So that would be like lining up the concrete trucks outside of the Aquatic Centre, all along Beach Avenue, right through along Denman Street, and all the way back to Stanley Park. So it's quite a significant amount of concrete we're producing and using in our city every single day, as well as across the province. So to summarize quickly the concrete situation, our annual cement production in BC is 2 million tons, and that's producing the 15 million tons of concrete. Both slag and fly ash are available. Speak to your supplier about what they have, and speak early. So particularly because slag you can generally include in slightly higher proportions for the stability of the mix, or alternatively, speak to your supplier just about the embodied carbon of the mixes they have and let them worry about the SCMs, but both are available. And then for the structural engineers that are writing specifications, specify UL cement if you're in BC, because it's likely what you're going to get. And for the sustainability consultants, take advantage of that, because again, it's a no-cost inclusion for your when accounting for your embodied carbon. Okay, moving on to steel. As I've kind of touched on before, there are two ways of making steel. So along the top here is the method, the blast furnace, or the basic oxygen furnace method. So taking raw materials, iron ore, limestone, and coking coal, heating up to 1,700 degrees in order to turn the iron ore into what we call virgin steel. It's an energy-intensive process because you are converting that raw material into steel. Compared to the bottom line there is the electric arc furnace method, which takes scrap steel and then effectively melts it down using an electric arc, and then turns that back into new recycled steel. So we in Canada use about 13 million tons of steel annually. And I've certainly seen quite a lot of debate about electric arc furnace steel and BOF steel and which one is better. So on the left-hand side is the carbon intensity of Canadian produced BOF steel in grey, and then similarly the Canadian produced electric arc furnace steel. And they are generally slightly better than the global average, both of them. And an electric arc furnace steel, the EPDs will show you being at about a third of the carbon emissions of BOF steel. So an easy conclusion to draw would be just specify EAF steel, but I'm here to tell you that's not necessarily always the right answer. And the reason for that is that globally, we are in a situation where we use more steel than we can supply from scrap and electric arc furnaces. So right now, only about a third of the steel that is used can be supplied using scrap electric arc furnaces. So somewhere in the world, if you're using electric arc furnace steel, somewhere somebody else is going to have to use virgin steel that they make in a blast furnace. So know that it may give you better looking results for your project when reporting, but it may not change global carbon emissions by specifying electric arc furnace steel. It's not just me saying it. So ArcelorMittal are one of the world's largest steel producers, and on their website, they very helpfully state that nearly all of steel is recycled. So when you specify recycled steel, you're not really changing the utilization of, or the likelihood that steel is recycled, because it's a valuable commodity that is recycled regardless. But they say even by 2050, only around half of projected global steel demand will be able to be satisfied using electric arc furnace recycled steel. Then back to this graph, which shows where the steelmaking plants are in North America. For people that are located in BC or on the West Coast, you may notice that there are very few steel skyscrapers, steel buildings in this part of the world, and a big part of the reason is that there aren't any steelmaking plants really to enable that to be the case. So concrete is the dominant material over in Vancouver. We have 13 plants in 5 provinces in Canada, and 6 of those plants are in Ontario. So a watch it very similar to mass timber would be, if you're using a high volume of steel on your projects, establish where it is being sourced from, because if it is being driven right across the continent, then there's going to be quite a big embodied carbon impact associated with that transportation. This is the global steel production map. So what we see is still quite a huge volume of steel being produced from China and Asia, and likely that is then being shipped to you on a boat, which has obviously better carbon emissions, but they may also have a dirtier grid. So taking that into account is important. I will say as well, it's the power of EPDs to really tell you what the carbon impact is of your materials. So this graph here shows the carbon intensity of electricity grids globally. And I would say that it is a little bit misleading. Graphs like this suggest that Canada and the US have very clean grids, and in Asia they have very dirty grids. But electricity grids are far more granular than maps like this show. So I just want to highlight to you as well this graphic, which shows the grid intensity of Canadian provinces relative to national averages. So that previous graphic was showing Canada having a very clean grid, but actually what we see at the bottom is Manitoba, Quebec, Ontario having relatively very clean grids based on hydroelectric power or renewable energy. But right up at the top, Saskatchewan and Alberta, which still have very fossil fuel heavy grids, actually having a much bigger impact, which then comes through EPDs to impact the A1 to 3 and the embodied carbon emissions of materials produced in those locations. So again, focusing in on steel produced in Canada. So looking at the Canadian national average electric arc furnace graph that I showed you previously, that had electric arc furnace steel about a third of the emissions of BOF. If we look specifically at a steel plant in Saskatchewan and you look at the EPD, you'll see that actually the steel produced there has a much higher emissions value than the average in Canada. So my messaging here is not necessarily do or don't use any particular steel. It's establish where your steel is coming from and look at the EPD and see how it compares relative to the average or the numbers that you're assuming. Canada imports steel from the US and China, and typically, as I say, on the West Coast, we see a lot of steel imported because it's not produced here. So this is a graph just showing the sources of where steel is coming from as a net balance into Canada annually. So a lot of it's coming up from the US. So to summarize on the steel, annual steel production of approximately 13 million tons in Canada, and only about a third of the steel we're using can be met by recycled steel. So feel free to specify it if that reflects what is available locally, but just know that specifying recycled steel alone is unlikely to change global global carbon emissions, and rather allowing a specification which includes both electric arc furnace and the basic oxygen furnace, but either sets limits for steel produced via either method, or limits the transportation, and accounts for A4 emissions is the smart way to do it. And my overall message as part of this whole presentation would be focus on reducing global carbon emissions over project emissions. And it's easier said than done, but often we're asked to report on project emissions, but really primary goal of what we're all doing is to try and reduce global carbon emissions. So that has to be the key. And then just to conclude on the three main materials, so mass timber, the supply isn't spread equally across North America, and in North America, transport is a significant part of the carbon story for mass timber. So engage early with suppliers, understand where your likely suppliers are, and take that into account when you're estimating what your embodied carbon will be. Often suppliers are very willing and open to engaging with you on how that material is delivered to site. And so if you have a client that is willing to do so, engage with them on that and seek to reduce as many trucking miles as possible where feasible, and either ideally use local supply, or if using from far away, enable shipping via rail or sea to minimize that upfront embodied carbon. And then for the concrete, as I say, there are 2 cement plants in BC, and most of the embodied carbon in concrete is associated with the cement. Take advantage of the limestone cement because it's likely what you will get if you're in the Pacific Northwest. Speak to your supplier early to understand either the global warming potential of the mixes or the SCMs they have available, and primarily reducing concrete volume is the absolute best way you can reduce carbon emissions. So that would be my big takeaway on concrete as well. And then on steel, know that electric arc furnace and blast furnace steel both have a place in the design space and in construction. It is, in my opinion, okay to specify either, but to specify them smartly so that you're encouraging suppliers to produce them efficiently. Establish where your material is coming from if it's steel and you're in the Pacific Northwest, and focus on reducing global emissions over project emissions. And that's it. Thank you very much. If you've got any questions, I'd be happy to answer them.
Thank you so much, Tom. That was an exquisite presentation. Great summary slide. Thank you again for pulling that together. So much good information and great tables, as was reflected in the chat. I'll start things off with the first material area. There was a question from Jeremy about, is CLT never transported by rail?
It can be, yes. So the material we used on Baker's Place that was shipped across from Austria, there a large part of the European transportation distance was done via rail. So the design was completed by the design team Equilibrium and in collaboration with the architect to utilize panels which fit into the containers. So an 8-foot wide by 40-foot long sea container or sea can. And if you're able to do that, then it's much more feasible to ship via both rail and sea. The rail network in Europe is much more widespread and established, whereas in North America, transporting in rail is more difficult, but it is still feasible. But that's where working the mass timber suppliers themselves are the right people to engage with early to establish what they can do. So Nordique have a rail track that goes right into their yard up in Quebec, and others, their objections are generally it's more costly to be double handling of material, having to move it onto a truck onto a railway, and then get it through the rail system and back out the other side. So depends a little bit, but it is feasible.
Okay, great. Over to you, Stephanie. Ask the next question.
Thanks. Yeah. Not going in order, but I will jump to the next one. I wanted to skip to the question from Iqbal about the emissions from he was asking about are cement emissions lower than the mass timber emissions then, if we were to consider Iqbal, I'm guessing if you mean like when considering the full picture of like where it's being sourced from.
Yeah, so it really depends. I think typically mass timber, it is most efficient to, for instance, in British Columbia, to use mass timber that is grown and produced in province and does not travel very far, and historically that has been what has happened and what is reflected in LCAs. So an LCA that accurately reflects where the CLT is coming from, if that has concluded that one material is better than another in either way, is likely very valid. I guess what I'm highlighting here is that because mass timber is produced in only a distinct number of locations, whereas cement production happens far more locally and widespread right across North America, it's likely that the thing to avoid is making an incorrect assumption that mass timber has been supplied locally, if that's not what ends up being the case. But wherever it is produced, if it is taken account of in an LCA, the results of that LCA should still be valid. So if it shows one material is better than the other, that is likely the case.
Okay, and I will jump in with the next question from Amy. What is the impact of recycled aggregate on GWP of concrete? Is it negligible? Is it important? What's that impact?
Yeah, so if I was to flick back to the graphic that showed the breakdown of embodied carbon of concrete by constituent. So the image on the right-hand side there is showing the aggregate. So the aggregate is a pretty small part of the overall concrete contributor. So the 90% in cement and 10% in aggregate. So recycling aggregate is a good thing if you have it and it is local. But if not the case, then I would suggest focusing on the cement is far more key, purely from a embodied carbon perspective. There may be other sustainability benefits from reusing aggregate and avoiding excavating new aggregate, but from a purely embodied carbon, cement is the place to focus.
Excellent. Yeah. We have a question also from Monica about can CLT be stood on end to use 10-foot wide panels in shipping containers instead of laying them flat at 8-foot wide?
Can it be potentially, when we've discussed it with suppliers, the logistics of sliding CLT into containers and dragging it out again means that generally it's the 8-foot wide dimension and laying them flat and horizontal, which is very much the common practice. So if you have a limited number of panels that are slightly larger, you can work with suppliers to do something like that. But generally, panels laid flat, limited by 8-foot widths is the norm for that reason, that it's just far more simple.
Mm-hmm.
And I should say, actually, you're not purely limited to shipping containers, so they can do what they call break bulk shipping. So for larger glulam beams, for example, they can ship just on a flatbed truck, not in a container. But it's just the material is a little bit more exposed and less protected during transportation.
Excellent, thanks.
I can jump in with a question and some reflections in the chat about more of emission factors. So Terry was speaking about how using 2018 figures for grid fuel is a bit misleading, as I think Alberta closed its last coal fire plant earlier this year. I recognize this stuff changes a lot, Tom, and it's very hard to keep all these great graphs up to date. I think a lot of reflection in the chat about how we measure things, how hydro measures their own emission factor. Do you have any reflections on some of that?
You're right, it's a very complex topic. So I think probably not to give any specifics, but more to say it's if you're asking those questions, you're asking the right questions. So to understand that there historically has been very drastic differences between, certainly in a Canadian context, the carbon emissions per kilowatt hour by province or by location. It's quite stark. So if even where provinces are reducing, that's brilliant, because that generally means everybody benefits. The operational carbon is benefiting, and also likely embodied carbon of things produced there is benefiting. But I would say I'm increasingly wary of national averages for materials or EPDs that use, when you look in an EPD, it will tell you the source of its data, and sources that use national averages for things, I'd start to become more wary of, knowing the picture of how varied things can be, both in Canada and the US by location.
Mm-hmm. Thanks, Tom. I have a question actually. Oh, you know what? Maybe before I go, I see a question that came in from Sam that says, regarding the upcoming shortage of fly ash as concrete additive, would tapping into wood ash produced in biomass burners be feasible? Also, very interesting point regarding the leakage of recycled steel and virgin steel. Yeah, thanks, Sam. So I guess this is more about using wood ash as a supplementary cementitious material. Is that possible?
That would probably be a question for somebody, a chemist at one of the cement suppliers. The cement industry is spending vast amounts of money looking at pozzolans and various future SCMs that are available. The challenge is making them available at scale to meet the demand. So let me see if I've got that graphic. So yeah, this graphic, which is showing just in the US, the amount of fly ash that was dumped, and that I know speaking to Heidelberg, is something they're looking at in the prairies. There are vast resources of dumped fly ash that is held. It was typically held in big ponds and lakes, and so there is quite a lot of potential for them to be able to excavate that material and use that in the future. But some of it has impurities in there that provides challenges. So wood ash may well be an option. I'm not familiar enough with the various ashes to be able to say exactly, but certainly know that a lot of the news that's coming out of the cement industry right now, as well as carbon capture, is also for use of alternate supplementary cementitious materials.
Mm-hmm. Awesome, thanks. Natalie, did you want to go next, or can I jump in? Thanks. The question I had was, and maybe this is more pertaining to concrete, if designers are sure they're going to use concrete in their building, and their baseline design has a specific volume of concrete, and then in their reductions, they optimize the design to reduce the volume. I've seen that from different case studies, which we'll be sharing, that sometimes even like a reduction there, you could just achieve 10% reduction and you're technically saving on cost. But if we were to go a step further and people were to track that A4 emissions from their baseline to their new design of volume reduction, could they show even greater than 10% reduction if they were to properly account for the baseline versus new design A4 emissions as well? I hope that made sense.
Sorry, Stephanie, there's a bit of background. The final part of your question was Could you
If I
possibly?
could even make it more, I guess the point is when you have a baseline design with a specific amount of concrete and your reductions are based on reducing the volume of concrete, if
Yeah.
you were to also be tracking your A4 emissions with your baseline versus your new design with the reductions, would you
Yeah.
see even more significant reductions achieved?
Yeah. I mean, if you're saying you've saved at A1 to A3 by reducing your material volume, then in theory you've also saved at A4 because you're trucking less of it. And I think, although this particular presentation didn't really touch on it, my background as a structural engineer, I would suggest, well, I would strongly recommend actually that the best way to initially start to reduce concrete emissions is to use less of it. So as structural engineers will know that making a flat slab is not the only way to make a slab, and we can use shape and form in order to use less material. But there are some other knock-on effects of slab overall thicknesses of floors or complexity in formwork. So there are reasons why right now the dominant thing to do is to build a concrete flat slab. But if reducing carbon is part of the driver, there are other forms and shapes and smaller grids and other ways that we can reduce material to just use less stuff. And I think we should be rewarding that when we're looking for reductions, to say projects have gone above and beyond in what they've done to just use less material.
Awesome. Thanks. Thanks, Tom. And, Natalie is just prompting me about a circularity question because I know that's often something that I like to ask about. But just for this, I saw another question come out. Maybe we'll have some other decarb lunches in the new year that are more circularity themed. Maybe what I would like to do is see that last question, although I don't have the initials KG, more about investing in slag. Like I see a few talking about just SEMs and other opportunities to scale that up maybe. And do you see, maybe this isn't necessarily exact that question, but if we were to know that in an industry that concrete has these high emissions from cement, is there not an opportunity? Is it not feasible if there's a driver to make actually scaling up lower carbon, like supplementary cementitious materials, so that we could actually see that flip in most of the concrete that is being used? The new standard is low carbon concrete.
Yeah, I mean, I think that there are a few ways to approach it. The most simple way that designers can achieve low carbon concrete is to set a global warming potential limit on the concrete they get and leave it up to the concrete suppliers to use their knowledge of their supply chains and the chemistry involved to produce products that can achieve that. I would suggest, so fly ash and slag have historically had effects on the way concrete gains strength and typically slows that down. So some of the hesitancy of increasing their use too much is because a contractor would still want to strip forms and stick to the same construction schedule that they have previously. And the concrete industry, as I say, is investing millions of dollars looking into the mixes that they produce in order to produce mixes which have less embodied carbon in them, but still provide the same strength, overall strength, early age strength, durability. So my recommendation would be, as designers, to specify global warming potential limits where that is appropriate for your geography. So in BC, there are EPDs, like vast numbers of EPDs have been produced over the past few years. So it is very easy for us to specify a global warming potential and the supplier to demonstrate that they're hitting it. If you're in a slightly more a different geography where embodied carbon measurement is a little bit more primitive, there you may need to specify exact fly ash and slag volumes.
Okay, with that, we're going to close things up exactly 1 o'clock. Thank you so much, Tom, for offering all your knowledge on the topic. I think that everyone came away with at least a lot of reference to these tables. I think they're going to be in high demand when we eventually publish those. So just to wrap things up, I wanted to highlight that there's going to be an embodied carbon exchange happening next Tuesday. So sign up for that on the Green Building calendar. I think Stephanie just threw that into the chat. Thank you, Stephanie. Also, there's going to be an embodied carbon social. So if you're in Vancouver and you'd like to just hang out with some embodied carbon nerds like ourselves, you are more than welcome. We're going to publish that in the coming few weeks. It will likely happen before the holidays. So just keep your eyes open for that invite. And then we're going to have the awards next year. We've had so much positive feedback about the CLFBC awards in general. So start thinking about projects that you want to apply with. So that's all. I'll leave it there. Thank you again, everyone, for attending today. Thank you, Tom, so much for sharing on this topic. And that's it for today. Have a great rest of your day.